Francis turbine. See, this is the question 18.23. So a Francis turbine with an overall efficiency of 75% is required to produce 148.25 kilowatt power. It is working under a head of 7.62 meter. Then the peripheral velocity is 0.26 root of 2gh and the radial velocity of flow at inlet is 0.96 root of 2gh. The wheel runs at 150 rpm and the hydraulic losses in the turbine are 22% of the available energy. Assuming radial discharge, and determine the guide blade angle, the wheel vane angle at inlet, determine the diameter of the wheel at inlet and width of the wheel at inlet. So here the turbine is Francis turbine. So what do you mean by Francis turbine? So you have to know what is Francis turbine. Francis turbine is an inward flow reaction turbine having radial discharge at outlet. So Francis turbine is an inward flow reaction turbine. This is very important. Inward flow reaction turbine, and the discharge at outlet is radial discharge at outlet. So this turbine is called a Francis turbine. Inward flow reaction turbine, and radial discharge at outlet. It is called a Francis turbine. Okay. So what do you mean by inward flow turbine? Okay. So here I will show you the picture of. This is the picture of inward radial flow turbine. So you can see here this is the guide vanes, and here this is the moving vanes. Okay, so here two vanes are there, guide vanes and moving vanes are there. Okay, we will explain. Okay. So the guiding wheel Okay, so the guiding wheel consists of the guide vanes which direct the water to enter the runner, which consists of moving vanes. Okay, so here this consists of a guiding wheel which consists of the guide vanes which direct the water to enter the runner, which consists of the moving vanes. Okay, so here you can see the guide vanes and moving vanes. So guide vanes and moving vanes. So the guide wheel consists of the guide vanes, which guide vanes direct the water to enter the runner, which consists of the moving vanes. The water flows over the moving vanes in the inward radial direction and is discharged at the inner diameter of the runner. So here the outer diameter of the runner is the inlet and the inner diameter is the outlet. So this is very important. The outer diameter of the runner is the inlet and inner diameter is the outlet. So here this is the outer diameter of the runner. You can see this is the outer diameter of the runner. This outer diameter is the inlet and this inner diameter is the outlet of the runner. So this type of turbine is called a inward radial flow turbine. Okay. Then another important thing is the classification of turbine. I have already explained that what do you mean by impulse turbine. Then there is a turbine called a reaction turbine. Okay, so in reaction turbine, the water possesses kinetic energy as well as pressure energy of the turbine is known as a reaction turbine. Okay, so the water possesses kinetic energy as well as pressure energy. Then the turbine is known as a reaction turbine. Okay. And what do you mean by radial flow turbine? If the water flows in the radial direction through the runner, the turbine is called a radial flow turbine. Okay, so that is the difference between reaction turbine, impulse turbine, radial flow turbine. Okay, so the Francis turbine is an inward flow reaction turbine and having the radial discharge. So I have already explained what do you mean by what is inward flow reaction, what do you mean by inward flow turbine, then what is the reaction turbine, then the discharge at the outlet is radial discharge. So these three conditions are there while we are dealing with the Francis turbine. Okay, then we will move into the problem. So here the overall efficiency is given. Overall efficiency is 75%. So you can see right here overall efficiency is equal to 75%. Then this overall efficiency is required to produce 148.25 kilowatt power. Okay, so power produced, that means shaft power, that is equal to 148.25 kilowatt. Then it is working under a head of 7.62 meter. So head is given, so right here head is equal to 7.62 meter. Then the next is the peripheral velocity. Peripheral velocity means that is u1, that is 0.26 into root of 2gh. So 0.26 into root of 2gh, substitute the value of g and h. G is 9.81, h is 7.62, so you will get 3.179, the value of u1. Then the velocity of flow at inlet, so that means vf1. vf1 indicates velocity of flow at inlet, vf2 means velocity of flow at outlet. So here vf1 is 0.96 into root of 2gh, substitute the value of g and h here, 9.81 into 7.62, you will get the value of vf1 is 11.38. Then the wheel runs at 150 rpm, so here n is equal to 150 rpm, and the hydraulic losses in the turbine are 22% of the available energy. So right here the hydraulic losses is equal to 22% of the available energy. Then assuming radial discharge, so radial discharge, this is the condition, this is very important. Radial discharge, Vw2 is equal to 0 and Vf2 is equal to V2. So this is the condition of RD, that means radial discharge. This is the condition of radial discharge. Vw2 is equal to 0 and Vf2 is equal to V2. Then the equation of hydraulic efficiency is given by total head at inlet minus hydraulic loss divided by head at inlet. Okay. So the hydraulic efficiency is equal to h minus, h is the total head. Okay, so this is the h, so that h is the total head, and the hydraulic loss is 22% of the available energy, that means 0.22 h, and head at inlet h. So you will get hydraulic efficiency is equal to 0.78. Then there is an equation of hydraulic efficiency that is equal to, so this is very important, Vw1 u1 divided by gh. This is the equation of hydraulic efficiency, Vw1 u1 divided by gh. So Vw1 u1 divided by gh is equal to, so it is given, it is you have find out this value 0.78. Then you have to find out the value of Vw1, so 0.78 into g into h divided by u1. Okay, so you will get the value of Vw1. Okay, so this is the velocity triangle of Francis turbine. Okay, so this is the velocity triangle, this is the velocity triangle of the Francis turbine. So you have to draw this. So this is the velocity triangle at inlet and this is the velocity triangle at outlet. So here the outlet is actually radial, that means Vf2 is equal to V2 and here Vw2 is equal to 0. Okay, so this is the condition here, Vf2 is equal to V2 and Vw2, the value of Vw2 is equal to 0. Okay, then first you have to find the guide blade angle. Okay, so you can see the guide blade angle. So guide blade angle is equal to alpha. Okay, so you have to apply tan alpha. So tan alpha is equal to opposite side by adjacent side. Okay, opposite side is Vf1 divided by adjacent side is Vw1. Okay, so tan alpha is equal to opposite side divided by adjacent side. Yes, so opposite side is this one Vf1 and adjacent side is this one Vw1. So Vf1 divided by Vw1. So find the value of this alpha. Okay, Then the vane angle at inlet, so vane angle at inlet is theta, so again tan theta is equal to opposite side by adjacent side. Okay, so opposite side is Vf1 and adjacent side is this one, so that means Vw1 minus u1. Okay, so you will get the value of theta. So this is the, you will get the value of theta. Okay, opposite side by adjacent side. Vw1 minus u1 is the adjacent side. So this is the opposite side, this is the opposite side. Okay, this is the opposite side. Okay, so this is the opposite side and this is the adjacent side. Okay, then so you get theta. Then diameter of the wheel at inlet, so the equation is u1 is equal to pi d1 n by 60. Okay, so this is the equation, u1 is equal to pi d1 n by 60. So n is actually given, so u1 you have actually find out, then the value of d1 is 60 into u1 divided by pi into n. So you will get the value of diameter of the wheel at inlet, 0.407. Then the width of the wheel at inlet, so the equation overall efficiency is given, so overall efficiency is equal to shaft power divided by water power. That is the equation of overall efficiency, shaft power by water power. So shaft power is given, it is 148.25. so here the shaft power is given, it is 148.25. then the water power is equal to, the equation of water power is rho g qh by 1000, rho g qh by 1000. So you have substitute the value of everything, you have to substitute the value here, and you will get the value of q. Okay, so you have to find out the value of q from here, from this equation. Okay, so overall efficiency is given, shaft power is given, so water power equation is rho g qh by 1000. So the unknown term is actually q. Okay, so the unknown term is q, so you have to find the value of q. Okay, so the value of q is 2.66 per meter cube per second. Then this is another equation of q, so that is equal to q is equal to pi d1 v1 into vf1. Okay, so you have to substitute all the values q, d1 and vf1 and find the value of b. So you can see the value of b, that means the width of the wheel at inlet is 0.177 meter. Okay, so this is the problem related to the Francis turbine. Then I will give one question as a practice question, as a homework question. Okay, so you have to solve the question from June 2017, question number 7. Okay, so question number 7. Okay, so here the question is, a Francis turbine develops 160 kilowatt, so power is given, so this is actually the shaft power, so this is shaft power, then this is at 150 rpm, so n is given 150 rpm, then head is given, h is equal to 10 meter, the peripheral velocity and the flow velocity is given. Okay, 0.3 into root of 2gh, the whole raised to 1 by 2, that means root of 2gh. It is velocity at inlet, peripheral velocity, and this is the flow velocity. Then the overall efficiency of the turbine is 78%, and this hydraulic efficiency is 82%. Then draw velocity triangle, you have to draw the velocity triangle and find guide blade angle, then vane angle at inlet, and diameter and width of the runner at inlet. So this is the question. This question is actually similar to this question, so here the overall efficiency is 75%, in this problem the overall efficiency is 78%. Okay, then the power is 148.25, so here power is 160 kilowatt, power is 160 kilowatt. Then the head is 7.62 meter, so here the head is 10 meter. Then the peripheral velocity is equal to, that means u1 is equal to, peripheral velocity u1 is equal to 0.3 into root of 2gh, and the flow velocity at inlet, so here the flow velocity of flow at inlet is 0.96 root of 2gh, here this is 0.9, here it is 0.9 in the root of 2gh. Okay, so that this is vf1. Okay, then the overall efficiency is 78%. Here the overall efficiency is 75%. Then the hydraulic efficiency is 82%. Here hydraulic efficiency is not directly given. Here hydraulic losses is given. Okay, but here the equation of hydraulic efficiency is vw1 u1 by gh. So here you have to apply this equation directly. So hydraulic efficiency is given. The hydraulic efficiency is 82%. Okay, 0.82. Draw velocity triangle. So draw velocity triangle means you have to draw this triangle. This is the velocity triangle of Francis turbine. And find the guide blade angle. So the guide blade angle is actually alpha, so you have to find out the value of alpha. Then runner vane angle at inlet. Runner vane angle at inlet means the wheel vane angle at inlet, that means theta. You have to find out the value of theta. And the diameter and width of the runner at inlet. Diameter of the wheel at inlet, so you have to find out the value of d1, and the wheel of the wheel at inlet, you have to find out the value of b1. Okay, so you have to solve question number 7. First you have to solve the problem of question number 18.23. then you have to solve the June 2017 question paper. This is the question number 7. Okay, so you can see the marks for this question is 10 marks. Okay, so solve it.